All right, next up, we got different types of reactions, right? So we covered this stuff already from chapter 4 and the stoichiometry and other videos. We'll be focusing on essentially types of reactions for this type of video. So there's 3 main types of reactions. There's a precipitation reaction, an acid-base reaction, and then a redox reaction, right? Obviously, this is just sample. There's many other types of reactions out there, but these are the 3 main ones. So let's talk about, first up, we have precipitation reactions. Precipitation reaction. Let's move this here. Number 1, precipitation reactions. So what happens in a precipitation reaction? You take 2 beakers filled with some kind of dissolved liquid, you pour one into the other, and then you end up with some sort of solid formed, or a precipitate, right? This solid is known as a precipitate. So how do you know if a precipitate is going to form? Well, if you look up here, you have to memorize the required solubilities. So there's really not that many that you have to memorize. So they are AgX, so silver X, Hg2X2, so mercury X2, and PbX2, so lead X2, where X is equal to chloride, bromide, or iodide, right? So these all will form a solid. So let's take a look at one example. Oh, wait, we got some more. 2 more. Barium sulfate and lead sulfate as well. So just those. There's really not that many memorized, so just memorize those. So let's take an example. So if we had barium chloride plus maybe some sodium sulfate, and then you'd see some kind of arrow, and then the rest would be blank. So the first thing to figure out is what the products could possibly be. And to do that, you're basically going to mix and match the cations and the anions. So you're going to swap them out for one another. So the first swap out we can see in purple here forms NaCl, sodium chloride, and actually 2 of them. The second swap out that we can see here in orange is barium sulfate. So that's your products they're going to form, and then you have to think about your solubilities. Anything not listed in your solubilities for the purposes of this class is soluble, right? So this would then be aqueous, this would be aqueous, this would be aqueous. But then this guy right here, you know from memorizing your solubility rules that this will be your solid. So this right here is your precipitate, your solid. And so the main thing you kind of have to think about these things is what's actually in solution. So if you have barium chloride in solution, for example, you don't actually have molecules of barium chloride. You've got barium 2+ and chloride minuses just kind of floating around in solution, pretty separate from one another, right? And then you have here, you have some sodium and some sulfate floating around. Whereas on this side, we still have the sodium and the chloride floating around in solution, but now the barium and the sulfate have formed a solid, so they are not floating around. It exists as barium sulfate. And so to get to the net ionic, the most commonly asked question is we take a look at what are our spectator ions. What are the ions that are doing nothing? And the things that are going to show up on both sides of the equation exactly the same. So in this case, it's this chlorine here, and then this sodium here, right? Both of them exist on both sides of the equation as the same thing. So they're not really doing anything, they're just spectating. So the net ionic only shows what's actually going on. So barium 2+ and sulfate 2- are acting to form a solid barium sulfate. So that's your net ionic equation. So that pretty much covers precipitation reactions. Next up, acid-base reaction. So for this one, I just want you to be able to point out what is the acid, what is the base, right? And so if you remember, an acid is an H plus donor, and then the base is the H plus acceptor. Right, so one's going to donate an H plus, and then the other one's going to accept the H plus. The H plus is moving from the acid to the base. So for example, HCl plus H2O can form H3O plus and Cl minus, right? So we see here that we have a product, we have a plus, and then we went from 2 H's to 3. So overall, net, this molecule gained an H plus. It gained an H plus. And what was this molecule originally? Well, it was water. So the H plus went to here, to the water. And you can see the Cl minus lost an H plus. So in this case, this is the acid, and this is the base, right? You know this is an acid pretty simply, because if you know the nomenclature of this is hydrochloric acid. Let's take a look at another example. NH3 plus water goes to form NH4 plus OH minus. So again, what we're looking at is where the H plus go. Well, we see a plus here, and this went from 3 to 4 H's. So we know that this molecule gained the H, so it's the ammonia that gained the H. So an H went from the water to the ammonia, right? So NH3 became NH4 plus, and then this water lost an H plus, so it becomes an OH minus, or a hydroxide. So in this case, this is the base, and then this is the acid. So you can see, you don't really have to know this, but a water can be an acid or a base. All right, so that takes care of acid-base reactions. Finally, we have redox reactions. In addition to redox reactions, really what you need to be able to do first is this: identify the oxidation numbers, or the oxidation states. So the oxidation numbers / the oxidation states will be quite important to be able to do these types of problems. So let's take a look at some of those rules, right? First of all, remember what oxidation number is, and it's the charge if the compound was ionic. So we're going to pretend basically everything is ionic, and we're going to say, well, if it was ionic, this is what the charge would be. So just some rules that you need to kind of memorize / know is a element, or a pure element, or a diatomic gas has an oxidation state of 0, right? So if you have pure copper as a solid, that oxidation state is 0. If you have Cl2, that's a diatomic gas, its oxidation state is also 0. Next thing you need to know is that the sum of the oxidation numbers is equal to charge. So something like water, you can see it has no charge. And so these oxidation states must sum to equal 0 to have no charge. So it ends up that each H is +1, and then the oxygen is -2. So that ends up being 0. Something you have to be careful for is something like a polyatomic ion, like nitrate, right? This has a negative charge, and so the oxidation state of this nitrogen and 3 oxygens must sum to be -1. So then just some common oxidation numbers that you want to remember that'll help you out. Right, so anything in group 1. So for example, hydrogen, lithium, sodium, potassium, cesium, all that kind of stuff. Hydrogen's a bit of an exception, will be +1. Always +1. And the exception there is hydrogen. Hydrogen, we'll see later on, can have a variable charge. Another thing we know is group 2 is always +2. Right, so that's your beryllium, magnesium, calcium, strontium, barium, that kind of thing. They're always gonna be +2. And then finally, we know that aluminum is always going to be +3. So that's good there. Some other things you need to know, probably the most important one right here is oxygen is -2, right? Except with fluorine, in which case you kind of have to figure it out. And for our class, this is pretty much almost always going to be true. The exception is peroxides. In which case it has a -1, but you don't have to know that. Just know oxygen's -2 except when with fluorine. Hydrogen is +1 with nonmetals and -1 with metals. So if you think back to the periodic table, there's a little staircase that kind of goes down here. These guys up here are nonmetals. Thus, everything down here is going to be metals. And then finally, the last thing is halogens, right, are -1 except with oxygen. Then they can change. So halogens are over here, -1. So chlorine, bromine, iodide. Fluorine won't be, is an exception to the -1 with oxygen, but chlorine, bromine, iodide, they're all going to be -1 except one with oxygen. Fluorine is almost always going to be -1. And so the last kind of thing you want to think about is getting things to their preferred charge. So if you don't have anything else, any other piece of information, nitrogen is probably going to be -3, but not necessarily. Sulfur is probably going to be -2, but not necessarily. You want to make sure you use all these rules first, and then if you can't, then you can start kind of going through some stuff. So for example, like KNO3, we know potassium is a group 1 metal. So potassium's right there. So it's going to be +1. We know oxygen is always -2, right? And then we know there's no charge here. There's no charge here. So these all must sum to be equal to 0. And so we know we have 2 of these. And then the last thing we kind of have to solve for is what is nitrogen? What is nitrogen? And so if you solve here, nitrogen ends up being +3, right? 1 + 3 - 4 is equal to 0. Take a look more examples in your notes, in the homework, etc. I won't do any more examples in this video. So first thing you have to do is be able to identify oxidation state. Next thing you want to tell is identify the oxidant and the reductant, or the oxidizing agent, reducing agent, or I could even ask you which part of the reaction is undergoing oxidation, which one is undergoing reduction, right? So redox reactions, right? Remember oil rig, oxidation is loss of electrons, right? So in this case, the oxidation number is going to actually increase. Reduction is gain of electrons. So in this case, the oxidation number is going to decrease, right? And that's because electrons are negative. So when you gain electrons, your oxidation number goes down. When you lose electrons, your oxidation number goes up. So let's just take a look at a pretty simple example. So we have zinc plus HCl going to zinc chloride and hydrogen gas. So let's figure out what this stuff is. So we know from one of our rules that anything by itself is simply 0. Right? We know hydrogen with nonmetals is +1. We know chlorine prefers to be -1, and that works out perfectly because it's what it needs to be for this thing to be 0. Again, we know chlorine is generally -1. And in this case, we have 2 of them. In order for the molecule to be neutral overall, zinc here must be +2. And then hydrogen, finally, we know anything in its elemental state is automatically 0. So if we connect the dots here, the oxidation number of zinc has changed. The oxidation number of chloride or chlorine has not changed. So chloride, chlorine, it's not really participating in this redox reaction. And then finally, the oxidation number of H has changed. So it's a redox reaction. So something's always got to be reduced. Something's always got to be oxidized. It has to balance each other out. We can't just arbitrarily destroy electrons. So here zinc is going from 0 to 2 plus. So it goes from 0 to 2 plus. It must have lost electrons since it's negative. And if you think about oil rig, its oxidation is lost. So here we write oxidation. And then on this other case, we go from +1 to 0. We got more negatives, so that means we gained negatively charged electrons. And so reduction is going on here. But generally, when you're talking about this stuff, you don't talk about whether it's undergoing oxidation or reduction. You talk about what it's doing to something else. Is something a reductant or an oxidant? So again, zinc is getting oxidized. It's losing electrons, but those electrons have to go somewhere else. And so they go to another atom. That other atom is then reduced. So what zinc is doing, it's reducing other atoms. So it's called a reductant. Zinc is the reductant. It's giving electrons. It's reducing something else. And thus, vice versa, this hydrogen is the oxidant. The oxidant, right? It's gaining electrons. It's taking that from somewhere else, so it's oxidizing something else. So another difference between reductant, oxidant, be able to calculate oxidation states. That'll be a big part of the test. That's really something important to know. You should be very, very familiar with redox reactions. And that's it for this video.